Differentiation is a powerful concept used in mathematics to determine the maximum and minimum values of functions. It is the algebraic method of finding the tangent to the function at any point. The derivative is a concept that is at the root of calculus. Differentiation is seen as an indispensable tool in every branch of science and engineering.
Here is some simple examples of differential equations which I'll be showing you how to solve. So for the first one, we have 6x cubed plus 2x squared plus 3x plus 2. We then go to the next line and write f dash x to show it's our differential. So we first have 6x cubed. So we'll bring down the power, which in this case is 3, and times it by the 6, which therefore becomes 18. We then minus 1 from the power, so it becomes 18x squared. This same method is followed throughout the equation. So for the next part of the equation, we have plus 2x squared. We bring down the 2, so 2 times 2 is 4x, because you 2 minus 1. The next part of the equation is 3x, which when we differentiate it, 3 times 1 is 3, and there is no x, so it becomes 3. The last part is 2 times 0, because there is no x, so therefore that is removed. So in the end, we have 18x squared plus 4x plus 3.
Many engineering problems involve the rate of change of a quantity with respect to another. Thus, it is necessary to incorporate derivatives into the equations used to solve these problems. Such equations involving derivative terms are known as differential equations. Differential equations will often be accompanied by one or more conditions which, once the general solution to the equation has been found, can be applied to attain a unique solution. In civil engineering, beams are designed to cope with the worst-case scenarios of loading, for instance, the largest bending moment and shear force that a beam undergoes. It is therefore important that we calculate these maximum values. If we have a beam under a specific loading condition, we can form an equation for the displacement under load, incorporating differentiation to find the maximum values. For our case, we will be looking at the bending moment and deflection of a cantilevered T-beam.
To find the equation for deflection, we first need to sum the moments, which will be equal to 0. This will give us our new expression for bending moment, which will finally be equal to negative force times length minus x, x just being any point on the beam. We can substitute this into our equation to find deflection. We need to integrate twice, but first we prove that c is equal to 0. At the fixed end of the beam, it resists rotation. So the slope is going to equal 0, and we can substitute this value in for x. By subbing this value in, we can find that c is equal to 0 as well. After integrating a second time and showing that c is equal to 0 again, we can find our final equation for deflection by rearranging. We can simplify this by factoring an x squared out. However, since our point load is at the end, x is equal to L. So we can simplify our equation even further to force times length cubed divided by 3 times Young's modulus times second moment of area. In our example, we have a cantilevered T-beam. We're given a second moment of area, which is equal to 196 times 10 to the 6 millimeters to the fourth. Length is also given at 3.5 meters, and we have a point load at the end of 14 kilonewtons. We also need a value for Young's modulus, which is equal to 200,000 newtons per millimeter squared. We can substitute these values into the equation we found before for deflection, which will give us a final value of 5.1 millimeters.